All right, let's look at this problem called lowest common ancestor of a binary tree. This is a classic tree problem which is quite commonly asked. So we are given a tree and we are given two nodes P and Q, and it's guaranteed that P and Q are present in the tree. We have to find out the lowest common ancestor. So this is one example. Here P equals to 5, Q equals to 1. So 5 and 1, the lowest common ancestor is 3. In this example, P is 5 and Q is 4, so between 5 and 4, the lowest common ancestor is obviously 5. So how can we do this? Let's talk about the most simple approach to do this, and very easy to understand as well. So let's come to the whiteboard. Let's look at the tree first. So the tree that is given, I will draw it out here. So you have 3, 5, 6, 2, 1, 0, 8, and 2 also has 7 and 4. And you're looking for the 5 comma 1. So you're finding LC for 5 and 1, and LCA for 5 and 1 obviously is 3. Like there is no doubt there. So how can we do that? One way is simply to look at the paths from the root node to these P and Q nodes, right? So if you look at the path to 5, you have 3 to 5. And similarly, if you check path to 1, you have 3 to 1. So this is matching and this is not matching. So the last guy that matched is the LCA. That's the logic, right? Let's look at the other example, which is 5 and 4. So LCA 5 comma 4. So you check your path to 5, and path to 5 is obviously 3 5, and then you also check your path to 4. So your path to 4 is 3 5 2 4. So till 3 everything matched, till 5 everything matched, and then there is no match. So the last guy that matched is 5, and so 5 is the LCA. That is the logic. Obviously, to save the pass, you will need some extra space, but that is the most basic, easy to understand algorithm. So why not let's implement this one first. All right, so the drawback sort of is, okay, you are finding P, you're finding Q, then you are matching their path. So you are doing the iterations in the tree two times, and you're iterating the path one. So you're doing sort of three sort of iterations, and then you're saving space, that sort of a thing. But still, like I said, easy to understand. So why not implement this algorithm first? So there, now we are on coming to the code. Let's see what we want to do. So let's say we take a list tree node and we call it path to P, and we do something like, hey, give me path from root to P, right? And let's say there's a magic function that does that. Then you go list tree node, hey, give me path to Q. I will get my path from root to Q. Now I just have to look at these two paths, and based on these two paths return the last matching. So last matching, let's define this last matching as maybe null to begin with. And so what we'll do is let's have the iterators. So I'll have iterator tree node, let's call it p iterator is, so I will have this path to p, and I'll get an iterator from this. Let's get similarly an iterator to walk through the queue path. So queue iterator would be path to queue. Now, while we have something, so the iterator has something, and the queue path has something. So we'll do tree node. Let's call it p node equals to p iterator.next, and q node equals to q iterator.next. Now, if these don't match, If p node and q node don't match, well, then you are done. Else you set last to the node and you will return the last matching guy, right? That's the general idea. Now let's also implement this function which helps us get the path. So we are saying I am going to get a list of tree nodes and function's name is getPath, where I will give you two nodes. One will be root and other will be the node, or let's call it target, right? And you give me the path from root to node. So if you are given to return a path, let's do let's call this path equals to, okay, let's save it in an array list perhaps, and then we will return this path. In between it's called maybe another utility function. So you do um, get path, root, target, and this path. Okay, and let's do this list tree node. Okay, so now you're not returning. So maybe initialize with void. You go get path. I have my root. I have my target, and I have my path. So my path would be this list. All right, so we'll try and search the node, and if we don't find it, we'll sort of backtrack, right? So, well, if so, we need to know if I, well, while searching, if I found the path, right? So maybe let's make it Boolean, and we go if the, well, if root is null, then I did not find it. Sorry about that. Otherwise, I want to see if I am this guy. So if root is equals to the target, then I have found it, right? So I'm gonna do, so in the path I'm gonna add myself. So path dot add root, and I'm going to return true as well. I have found it. All right. So if that's not the case, I have not yet found it. Then I'm gonna have to find it in my left subtree first. So let's find it in left. So root dot left get and path. But okay, before doing that, maybe add um, I think this path dot add root can be added here itself. So right, and if root is target, then we just return. And now we're checking. So because we want to add each and every node that we consider, and at the end, if nothing pans out, then we're going to do remove the last node if we didn't find anything. So which would be something like path dot one, and we're going to return false. This is uh, when it's not found, obviously, right? So first we try and find in the left subtree, and obviously if found, then we just return true, and if not found, then we try and search it in the right subtree. And again, if so, you could maybe, instead of doing if found or something, like you could just do uh, if you find it in the left subtree, then return true. And if you're here, that means you didn't find the left subtree, so you're going to try and search in the right subtree. And if you find it in the right subtree, then return true. And at this point, you haven't found it in the left subtree or the right subtree. That means it's not in the subtree down from this path, so just return false and consider the different path from its parent, that sort of a thing. So that's the logic. Let's run code and fix any issues. Okay, it gets accepted. Let's submit and see if all test cases pass. And it does seem to look like all test cases pass. So that's definitely one solution. Now to slightly better, let's discuss a slightly better algorithm, which essentially, okay, the overall complexity will still be the same, but just will avoid multiple iterations and avoid multiple like extra space that we were using for uh, saving the paths and stuff. Like without having to saving the paths, without having to do multiple traverses of the tree, we could do a slightly better approach. Let's discuss that. So basically, in that approach, we essentially look for any of the one of the nodes in the left subtree and right subtree, starting from the root node recursively. And if you find one of them, we just return that node. So let me give an example what I mean by that. So I come back to, okay, I'm already on the whiteboard. Let's see this tree, and we were searching for 5 and 1, right? So starting from 3, first we search the left subtree and we find this 5. So as soon as we find this 5, we just return this 5 right away. So and we don't traverse back. So basically we are searching for any of the two nodes, either 5 or 1. And if we find any one of them, we just return that. So when we do a search from 3, we get 5, we return 5. We don't traverse anywhere further down, right? And then we go from 3 to the right and we find a 1. And once we find a 1, and that's what we are searching for, that's another one. So we return that guy. So basically, when we call for left, we get 5. When we call for right, we get 1. And if there is a node for which the left call to the left and call to the right return two different non-null nodes, that means this node is the LCA. Let's look at the other example. Let's look at a few more examples to understand the algorithm better. So taking the same tree, so 3, 5, 6, 2, 7, 4, 1, 0, 8. The other example is 5 and 4. Okay, so let's look at, all right, let's bring it here. Let's make it slightly bigger, right? Now let's say we're trying to solve for 5 comma 4, right? So for 5 comma 4, again, first from starting from the root, we go to the left, we find 5. As soon as we find one of the nodes, we return right away. So for this path, we'll return 5 right away. Then we go to the right, we go to 1, 1 doesn't match anything. We go to 0, 0 doesn't match anything. If it doesn't match anything, eventually you will return null. So this guy will return null. So this guy will return null, right? So for 3, left returned 5, right returned null. What does that mean? That means in right, I did not find anything. In left, I found 1, 5. That means where is this other guy, 4? Obviously, it was not in the right, so it must be in the left somewhere below 5 because first I encountered 5. So that means 5 will be the LCA, right? Let's take a look at another example. So the same tree, you have 3, 5, 6, 2, 7, 4, and we go here 1, 0, 8. Let's say we are trying to do find LCA for let's say 6 comma 7, right? If you're trying to do 6 comma 7, so when we call for the right, obviously if you look at the right, none of the nodes are present in the right subtree. So eventually when you do the logic search, you will get null here, no doubt about that, right? Now what will the left subtree return is the question. So the left subtree, so if you go all the way down, 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 first 5 is not of our interest, then we would have gone to 6. 6 is one of the interesting guys, right? 6 is definitely one of the interesting guys. So this will return 6. And when from 5 when we go in the right direction, 2 is not interesting, 7 is interesting, 4 is not interesting. So this will return null, 7 will return 7. So for 2, what will 2 return? 2 will say, hey, my left subtree returned 7, my right subtree returned null. That means uh, I will return whatever I found. I found 7, so I will return 7. So this guy will return 7. So now for 5, you see one guy returns 6, other guy returns 7. So that's the node. For if that happens for any node, that means that is the LCA. So in this case, we'll mark 5 as LCA. So 5 will return itself, right? So the logic is if any of the child is null, then return the other child's value. If any of the child returns null, then return the whatever other child returns. It could be null, it could be non-null. If both child returns non-null, then return yourself as the LCA. That's the sort of the logic. All right, let's try to code this logic up. So come back to LeetCode. We reset the original code that we wrote, and we try and build that logic that we just played around with. So what we're saying is, if let's handle the base cases. Well, if my root is null, right, or I found one of the if I when I'm so if root is p or q, right, if I found it to be equal to one of any of them, then in all these cases return root, right? Otherwise, I'm going to call for my left and right child. So from left, what do I get? Let's see. So I do lowest common ancestor. I searched in left. So left, I'm searching for either P or Q. And from right, I go lowest common ancestor. Okay, now if both are not null, if left is not equals to null and right is not equals to null, that means this is the LCA, right? So that means you have to return root as the LCA. Else, if one of them is null, if left equals to null, well then you return right. Whatever right return, whatever the value. Okay, so return right. Else you return left. I think that's it. That's all we want to do. So let's run code and submit. And this gets accepted as well. All right.